For our competing species model, I'm once again going to keep it fairly simple, and I'm actually not going to make it too different from the predator-prey model in a couple of ways. Effectively, all I'm going to do is change some signs, SIGN, signs, positive or negative, of some constants of proportionality. I am going to use different letters X and Y, partially because that's what the book does, and partially because I'm not going to pretend I know what these species are. Just use more generic letters X and Y. X species and Y species. For the competing species model, one difference is I'm going to assume exponential growth for both species in the absence of the other one. And alpha times X for the dx dt equation and a gamma times Y for the dy dt equation. So both species will grow exponentially in the absence of the other one because they're not there to compete. You know, an example, I guess, could be like two different species of fish in the same lake, both that like to eat the same plant. Okay, that would be an example of a competing species. Another way to think of this is you even have exponential growth, at least approximately, as long as the populations are small. But they are competing, and the competition can be accounted for with minus signs in both interaction terms. A minus beta x to y here and a minus delta xy here. So what's the difference between this and the predator-prey? Besides using x and y instead of r and w, the negative sign that was there in the predator-prey became positive, and the positive sign that was there became a negative. I switched the signs in the dx dt equation, is what I did. How does that affect things? It does not change the equilibrium points. They end up being the same. I will once again give these functions names, call this f of xy and g of xy. I can factor f of xy as x times alpha minus beta y and factor g of xy as y times gamma minus delta x. The equilibrium points end up being the same when you set these equal to 0 and solve for x and y. You get equilibrium points at the exact same points as before. xy equals 0, 0, and gamma over delta, comma, alpha over beta. In fact, the nullclines are the exact same things as before as well. However, what changes is the directions of the vectors in the vector field. That changes. The nullclines are the same. So here's going to be my phase plane. I'll label the axes with x and y this time, though. The x nullcline, and yes, I do call it an x nullcline now instead of an r nullcline, is where dx dt is 0, which is going to lead to the vertical line x equals 0, the y-axis. Also, the horizontal line at y equals alpha over beta. The y-axis is an x nullcline, and a horizontal line at y equals alpha over beta. And the y nullcline will consist of two lines again, the same two lines as before. It's where y times, in parentheses, gamma minus delta x is 0, which occurs at y equals 0, which is the x-axis. Also a vertical line at x equals gamma over delta, the x-axis, and a vertical line at x equals gamma over delta. Where red and blue cross, where x and y nullcline cross, we get equilibrium points. Red and blue make purple. This is a purple pen, though it's hard to tell on the screen. Red and blue make purple. I'm having fun. But But what about the directions of solutions? Along the y-axis, where x is 0, dy dt is positive when x is 0, and y is positive. I move upwards. But something new here compared to the predator-prey is along the x-axis, when y is 0, x increases, so I move to the right, away from the origin, not towards it. That's something new. So again, two competing species. If one or the other is not present, you're going to get exponential growth in both cases. So I guess that must mean something different happens in here as well. That must be the case. Let's once again do our analysis about the signs of these things, starting with what happens when x and y are both large. And the sign is not determined by these things because we are just restricting ourselves to the case where x and y are positive, so I can ignore those things. If x and y are both large positive numbers, because you're subtracting positive constants times them, these both become negative when x and y are both large, meaning both dx dt and dy dt are negative, meaning they decrease, both of them. You have to have an arrow pointing to the southwest, down and to the left, because x and y are both decreasing when x and y are both large. On the flip side, if x and y are both small, close to 0, I've got positive numbers minus small positive numbers, making positive numbers. Dx dt and dy dt are both positive, and x and y are increasing. Something different's going on here. What about over here? X is large and y is small. X is large and y is small. X is large and y. If y is small, that's positive. And if x is large, that's negative. Dx dt is positive, dy dt is negative. X is growing, y is decaying. You got to go to the down to the right, southeast. And finally, up here, x is small and y is large. X is small and y is large. If y is large, I'm subtracting a large number. I get a negative number there. If x is small, I'm subtracting a small positive number giving me a positive number here. X is small and y is large. Dx dt is negative. Dy dt is positive. X is decaying. Y is growing. What kind of weird thing could possibly be happening with the solutions here? They're not going around either direction. I guess like this and like that, maybe. Yeah. It's a little bit more subtle. If my initial condition is, say, there, so that y is relatively small compared to x, I got to be going to the northeast. And I do have to cross the y nullcline with horizontal tangents. We still have vertical tangents along this x nullcline here and horizontal tangents along the y nullcline here. So I still have to cross that y nullcline with a horizontal tangent line like this before heading down that way, I guess. On the flip side, if x is fairly small compared to y, if my initial point is right there, I got to go to the northeast here and cross this x nullcline with a vertical tangent before going up this way, it looks like. And I hope it's intuitive that you're also going to be asymptotic to the axes. You don't cross the axes because you already have solutions along there. Not proving it, but that is the case. On the flip side, if you start up here, maybe right about there, x and y are both large, but x is a bit larger than y, relative to this picture at least. You got to go to the southwest and cross this with a vertical tangent before heading to the southeast. Start up here, head to the southwest before crossing with a horizontal tangent, and head to the northwest. And boy, how could there's a big difference between what happens here. There's got to be like a boundary between those two different kinds of behaviors. And yes, there is a solution that you might guess is straight. And I think it is for this example, though in general, it's not necessarily straight. Going from the origin up to this point, and also effectively from infinity to this point, that's kind of like the boundary between the two different kinds of behaviors. And there's also solutions that cannot be straight lines, actually, that are going to curve down this way and curve up this way. It's not a perfect drawing. Something about like that seems to be what probably has to be going on. And this solution curve that may be a straight line, though in general it's not a straight line, separates the plane into two different kinds of behaviors. And because of that, it's called a separatrix. I love that word. Separatrix. Actually, the two of them together are called separatrices. Yeah, as t goes to infinity, it's a very fine line between, and I mean that literally, a very fine line between the two different things that can happen. If you're down here, x is large compared to y. Both species grow at first, but then in the end, y goes to 0 and x grows exponentially. X wins. If you're up here, they both grow for a little while, but then x goes to 0 and y goes to infinity. Y wins. If you're up here on either side, both species are dying off for a while, but then in the end, either x wins or y wins. The moral of the story for real life application is maybe this could happen in real life. It's not like physics. It's not like making precise predictions about where Mars is going to be 10 months from now. It's about making rough guesses of what might happen. You know, it's so oversimplified compared to real life. These are just caricatures of real life. Maybe when you're in a situation with competing species, in the end, one or the other dies off. Could they both possibly reach equilibrium together? Boy, they'd have to be exactly on that curve to get up there. And that's not likely. So the moral is it's possible one or the other species could die off. But again, this oversimplifies reality. So you got to take it with a grain of salt. It's more like a maybe that could happen. Let's confirm with Mathematica. I do have x and y. I did change the negative alpha r to a positive alpha x. And I changed the plus beta rw to a minus beta xy. But it is the same equilibrium points as before. But the solutions do look different. It's reflected in this picture. Okay. You are seeing what I drew by hand. Equilibrium points are where the red and blue cross. Origin, you're right here. And like I emphasized on Monday, by doing this for arbitrary parameters, alpha, beta, gamma, and delta, you can also learn the lesson that, for example, if beta and delta stay constant, but alpha and gamma increase, the point's going to move away from the origin, that equilibrium. If beta and gamma are constants, but these increase, yeah, that's faster growth for small populations. That makes some intuitive sense that the equilibrium point would be further from the origin. On the other hand, if beta and delta increase where alpha and gamma are constant, then this point moves closer to the origin. If the interaction has big negative effects, or bigger negative effects, that tends to lead to smaller equilibrium points, smaller populations. NDSolveValue can be used again. And in this case, with the particular initial conditions that I picked, X is 0.11, Y is 0.1. Also notice I did choose alpha, beta, gamma, delta to all be ones here. Like that's arbitrary. I could have picked different numbers. With this particular initial conditions, it looks like X is growing exponentially in the long run and Y is decaying to 0. You could make regular plots of those. You could also put it in a parametric plot, and you could also animate it. And that's what I'm doing here. And when we animate this, we're going to see a subtlety that we cannot see from either the stuff we do by hand or what we've done so far in Mathematica. What is that subtlety? Let's play it. Watch the curve. It's tracing out. And yes, X is going to infinity while Y goes to 0. The subtlety I'm hinting at is the motion of the point on that curve is slow at first, and then it speeds up. That's reflecting X ultimately growing exponentially. The fact that it's speeding up. But again, if I picked a different initial condition, like if I changed X 0 to 0.1 and Y 0 to 0.11, I bet we get different behavior. Now, yeah, the point is going to go up that way. Could I make it go exactly toward the equilibrium point? With this particular example, I think I can. Going right toward the equilibrium point. That happens to be at the 0.11. It does happen to be a line there. That's a straight line solution. In general, the separatrices are not necessarily lines. They just happen to be for this example.